Good day, students. Welcome to Mathgotserved.com, where we don't just solve, we teach. In this clip, we're going to be going over problems 1 to 5 of the Geometry Common Core New York Regents exam for June 2016. At any point in time during this presentation, if you have any questions, feel free to ask your questions in the comments section below, and we'll be glad to provide you with support. Alright, let's take a look at question number 1. It reads, a student has a rectangular postcard that he folds in half lengthwise. Next, he rotates it continuously about the folded edge. Which three-dimensional object below is generated by this rotation? So one thing you want to keep in mind, a tip concerning rotating 2D figures, is that anytime you rotate a two-dimensional figure about an axis, you will always have a solid with a circular outline. Okay, you're going to see that the effect of that rotation on the solid. Okay, so in this situation right here, we have a rectangle, and then the rectangle was folded lengthwise. Now, if you fold a rectangle, depends on the dimension, you end up with either a square or another rectangle. Okay, so let's say we have this rectangle right here. Let me adjust the dimensions. Okay, and then what the student did is this person folded the rectangle lengthwise along the middle. Okay, so if he folds it like this, basically he'll end up with a folded a folded rectangle. So it's going to look something like this. Okay, so what this person did is he took this rectangle that's folded and then he rotated it the about the folded edge. So this right here is the axis of rotation. So this person rotated it around here. Now, since we're rotating it along the side, the correct answer should have a circular outline somewhere on the figure. Okay, so you're going to look at these four options. Which of them do not have any circular outline? Option 2 does not, and option 4 does not. So our answer is either option 1 or option 3. Okay? Okay, so here we have a GeoGebra visualization to help you visualize what happens when you rotate a rectangle about an axis. Okay, if the axis is on one of the sides. So let's go ahead and rotate this rectangle. Bam, there you have it. So what do we have here? This is a circular prism. Okay, or also known as a cylinder. Okay, so that clearly shows that our answer is option number 3. Okay, now if you look at option 1, what kind of shape can you rotate to generate a cone? If you take a right triangle and you rotate it about the altitude, one of the altitudes, you will end up with a cone. Okay, so this one has a triangular outline. So the rotation of a triangle, let me draw it for you. So let's say you take a right triangle of this nature and you rotate it about this axis, you end up with a cone. Alright, but if you take a rectangle or a square and you rotate it about one of the edges, you end up with a cylinder or a circular prism. Alright, let's take a look at question 2. It says a 3-inch line segment is dilated by a scale factor of 6 and centered at its midpoint. What is the length of its image? Okay, so one thing you want to remember is the meaning of dilation. Now, when you dilate an object by a scale factor, it simply means you're multiplying the lengths of that object by that scale factor. Okay, so if we have a line segment that is 3 inches, so let's say let's draw a 3-inch line segment right there. So let's say that's your 3-inch line segment, and you scale it up by a factor of 6. So let's say this is the center of the line segment right here. If you scale it up by a factor of 6, guess what? The image is going to be 6 times the length of this. Okay, so if the original length is 3, when you scale it by 6, scale in, let's erase that, scale in by a factor of 6, scale in by 6 is basically going to be the original length multiplied by 6. So 3 times 6 is 18. So we're going to have a new segment that is 18 inches long. And the answer is clearly option number 4. Alright, so let me show you a visual of the result real quick. So this segment right here is 3. So what you were simply going to do is take this segment and then you multiply it by 6. We're going to have basically 6 of this segment. Okay, so there you go. 1, 2, 3, 4, 5, 6. So basically, let me line them up, starting from the center right here, centered on this. So if I take 6 of these, stack them next to each other, question is, how long is it going to be? Okay, so 1, 2, and oopsie, let's change that, and 3. Okay, so this is basically the original segment of length 3 stretched scaled up by a factor of 6. Alright, so if we go ahead and count how many units that we have here, so if you simply count the number of boxes from start to finish, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Bam. So there you have it. Okay. So we have a segment of length 3 scaled by a factor of 6. This simply means you multiply the entire length by 6. And you end up with your final segment, which is 18 units inches in length. Alright, let's take a look at question 3. It said Kevin's work for deriving the equation of a circle is shown below. So we have, this is the original problem and these are his 4 steps, okay? The question is, in which step did he make an error in his work? So in this problem, he's basically converting this equation to the center radius form, okay, of the equation of a circle. And the question is, where did he make the mistake? Now, for some of you students, it's easy for you to examine the work of someone else and see what the mistake is. But if you're having difficulty with that, consider this tip on error analysis. A quick way to find the error in someone else's work is to solve the problem yourself. Compare your steps as you go, and where you have a discrepancy, more likely than not, that is where the error should lie. Okay, so that is what we're going to do here. I'm going to solve this problem. My goal is to convert this equation into center radius form as we have here. And as I walk through each of my steps, I will compare it with the work of Kevin and see if we have an agreement or not. Okay, so the problem is x squared plus 4x equals negative quantity y squared minus 20. So the goal, first of all, is I want to get all the variables on one side. Okay, I need the x's as a perfect square and the y's as a perfect square, both on one side of the equation, and then I'll have a constant on the right. Okay, so let me write down what our goal is so that you do not get lost. The goal is to write it in the form x minus h squared plus y minus k squared equals the radius square. This is known as the center radius form. Okay, that's the goal. Alright, so first thing I want to do, this is not, this y square is in the parentheses, but I need the square outside of y. Okay, so what I'm going to do is I need to resolve this parenthesis right here by distributing. Okay, so distribute this minus to y squared negative 20, and that yields x squared plus 4x equals negative y squared plus 20. That is step number 1. Let's compare what we have here. Do they agree? X squared plus 4x, x squared plus 4x equals negative y squared plus 20 equals negative y plus 20. We have an exact match. Step number 1 is correct. Alright, next thing that Kevin did, personally I'll do it differently, but this is what he did. So we're going to try and solve it following his direction. So he wants to complete the square on the left side since y is already a square. Okay, there's no other y here, so y squared stands alone, that's good. But we have x and an x here, so we need to create a perfect square trinomial for the x's. To accomplish that, we have to add b over 2 square to both sides of the equation and complete the square on the left side. When I'm talking about the b, I'm talking about the b of the x variable. Alright, there's an imaginary 1 here. That's the a for the x. This is the b for the x. In order to complete the square, we have to add b over 2 square. B of the x is 4. What do we do with that? We divide it by 2, which is 2. We square that, 4. This is a number we have to add to both sides in order to have a perfect square trinomial on the left. So let's go ahead and do that. We're now going to have, next step, x squared plus 4x plus that term that creates a perfect square trinomial on the left, which is 4. Now, this is an equation. Okay, since I added 4 to the left side, what must I do to the right in order for my scale not to topple over? I need to add exactly the same value. So I need to add 4 to the right side to compensate for the 4 I added to the left side so that this remains an equation. Alright, so this is step number 2. Let's compare our work with what Kevin did. X squared plus 4x plus 4, perfect. We have a perfect square trinomial on the left side. On the right side, negative y squared plus 20 plus 4 minus 4. Ladies and gentlemen, we have a problem. This is minus 4, and this right here is plus 4. Okay? This is incorrect. Remember, you have an equation. Whatever you add to the left side, you must add the same value to the right side, not subtract. Okay, so that you have an equation. So step number 2 is incorrect because Kevin subtracted 4 from the right side as opposed to adding 4. Answer is step number 2, option 2. Okay, let's take a look at number 4. It says, which transformation of segment OA would result in an image parallel to segment OA? Now, one thing you want to note is that the slope and the length of a line are preserved under translation. When you translate an object, you're just moving it around. Okay, you're not rotating it, you're not flipping anything. So the length stays the same and the slope stays the same also. Another thing you want to keep in mind is that when two lines are parallel, what does that mean? It means that their slopes are the same. Parallel means equal slopes. So what I'm going to do is I'm going to carry out these transformations to segment OA, and then we're going to see which one is the correct answer. Some of you might already discern that the answer is option A because that's the only translation that's there, and the slope is preserved under translation. Well, if that is what you're thinking, you are correct. Okay? But let's act as though we're not that perceptive, alright? I'm just going to carry out the transformations, nice little review on transformations, and then we will see which one is parallel or has the same slope as segment OA. Okay? Alright, so let's start with option 1. A translation 2 units down. Now, translation 2 units down means that this line shifts down 2 units, 1, 2. So we have a line segment like this. Okay, let's see. Goes up 1, 2. Goes up another 1, 2. And it goes up another. Let's see, something like that. Alright, okay. So just imagine you have this line right here. Shifted 2 units down. So this line segment, let me put it on there. So it's perfect. And I just shifted 2 units down, 1 place and 2 places down, like that. Alright, so translation, that's what it is. It's just a shift downwards, okay? So, you see, this is line number 1 here. So this is 1, option 1. Now, what's the slope here? The slope is you rise 1, you run, you rise 2, 1, 2, you run 1. So rise over run is your slope. You rise 2, run 1. What is the slope of the original line? You rise 2, you run 1. Slope is 2 over 1. What do you notice? These two segments have the same slope. Okay, well, let's do the other ones. We have a reflection over the x-axis. What will that look like? So if you reflect over the x-axis, it's going to look something like this. Change that. Make it a blue, red line this time. So reflection across the x-axis there. So you did the first one, do the second one, and almost the fourth one. Stop. Wait, let me see. Stop somewhere there. Okay. So there you have it. Now for this line, what's the slope of this one? This is option 2, right? A reflection about the x-axis. This has a slope of, you rise -2 and you run 1. Is it the same as 2 over 1? No. It's the opposite. So that's not the answer. How about option 3, reflection over the x-axis? Let's sketch that. Let me show you what that looks like. Some of you might already be able to visualize what that is. So if you reflect about the y-axis, so you're going to have 1, 2, 2, and then it goes up a little bit somewhere there. Okay, let's make sure it's correct. Okay, so something like that. So that's option 3. What do you notice about the slope of option 3? The slope of option 3 is actually from this point to this point, you fall 2, 1, 2, and you run 1. -2, the same slope as this one, right? But it's not equal to 2 over 1, so we can clearly see that option 3 is wrong. How about option 4, a rotation 90 degrees about the origin? So when you rotate this line segment 90 degrees about the origin, you're going to have something like this. 1, 2, 1, 2, and then the last one somewhere here. Okay, so it's going to look something like that. Okay, now what is the slope of this line that has been rotated 90 degrees? The rotation 90 degrees basically, let me show you something real quick. This angle right here is 90 degrees. That's the rotation we were talking about. This is option 4. What is the slope of this line? Slope of this line should be the negative reciprocal of this. Remember, if two lines are perpendicular, then the product of the slopes is -1, or the slope of one is a negative reciprocal of the other. Well, let's see if that's the case here. So the slope M is, you rise -1, go down 1, and you run 2. -1 over 2. That is not the same as this. So option 4 is not the answer. We can clearly see that option 1 is in fact correct. Alright, let's take a look at question number 5. It says, using the information given below, which set of triangles cannot be proven similar? Alright, so one thing I would like you to recall concerning similarity is that there are 3 similarity postulates and theorems that you want to keep in mind for the Regents exam. Okay, you have the AA similarity postulate, which basically states that if two angles of a triangle are congruent to two angles of another triangle, then the triangles are similar. You have SSS. If 3 sets of corresponding sides of 2 triangles are in proportion, then the triangles are similar. Okay, and you have SAS. If 2 corresponding angles of 2 triangles are congruent and the sides that is including that angle is between, if those sides are in proportion, then the 2 triangles are similar. Okay, so I'm going to show you a nice little shortcut you can use here. So based on what we have presented, we can see that we have a proportionality going on with the sides of these ones, and here we have congruency. Okay, congruency is basically one-to-one proportionality, so that counts too. So here we have side. So this side goes with this side right here. So we have side, and then we have angle, the B and the S, and then we have side. This is the second side. SAS. Is this valid, ladies and gentlemen? Is there any such thing as a SAS similarity theorem? The answer is yes. See that right there? So option 1 is good. Remember, we're looking for the one that cannot be proven similar. Option 2, we have angle, angle, that's an A. So angle C is congruent to angle N. We have another pair of angles, D and L are congruent, that's an A. We have AA. Is there any such thing as the angle-angle similarity postulate? The answer is yes. Option 2 is good. Option 3, we have angle. Well, let's reverse the order there. We have side. So this side right here is proportional to this side. You're multiplying by 4 here. I mean dividing by 4. So 32 divided by 4 is 8. 16 divided by 4 is 16 divided by 4 is 4. So ladies and gentlemen, we have a problem with the sides. These two sides are not in proportion. Okay, let's ignore that for a second. Let's just assume we have side. Okay, and assume that these sides were proportional, which is not. Okay, S, and then we have A. Is there any such thing as SSA similarity postulate or theorem? Is this valid? Look at this list here. The answer is no. So question 3 is the answer. This is not. These two triangles are not. You can't prove that these two triangles are similar with this information that is given. More likely than not, they're not. Okay? All right, let's just take a look at option 4. Option 4, this side right here, xy, is similar to this side. That's a 1-to-1 similarity ratio right there. So this side is congruent to that. So we have an S, and then let me put an S here. So, and then we have the angle X and S are congruent. You have A, okay, and then XZ and RS are congruent. They're in proportion, 1-to-1 proportionality. So we have S, A, and then an S. Is there any such thing as a SAS similarity theorem? The answer is yes, just as we concluded in number 1. So option 4 can be proven to be similar. Okay, in fact, they're congruent here. So option 3 you cannot, because there's no such thing as SSA or ASS. Okay, these two don't work for similarity or even congruency. Thanks so much for taking the time to watch this presentation. We really appreciate it. If you found the contents of this tutorial helpful in your review for the Regents exam, do give us a thumbs up. Your positive feedback is very important to us. Don't forget to subscribe for the remainder of this review series. If you have any questions or comments, place it in the comment section below, and we'll be more than glad to support you. Okay, more clips can be found on mathgotserved.com. Thanks again for watching, and have a wonderful day.